Have you ever wondered how an LED can blink automatically, or how a buzzer can turn on, after a short delay, without using any microcontroller or programming? What if I told you that all of this can be done using just one small integrated circuit? An IC that was invented more than 50 years ago, yet is still used today in electronics labs, projects, and products. That IC is called the 555 timer. In this video, we are going to understand what the 555 timer is, how it works internally, and finally, we will build one real project using it. No complex mathematics. No confusion. Just clear logic and real understanding. Let's begin. What is the 555 timer? The 555 timer is a very popular integrated circuit used to control time in electronic circuits. It can generate time delays, produce pulses, and create square wave signals. In simple terms, the 555 timer decides when something turns on, how long it stays on, and when it turns off. Because of this ability, it is commonly used as a timer, an oscillator, or a pulse generator. This single IC can replace many complex circuits, which is why it became extremely famous. Even today, engineers continue to use the 555 timer because it is simple, cheap, and reliable. It does not need software. It does not need programming. It works purely with analog electronics. For beginners, the 555 timer is one of the best ways to understand timing, comparators, and basic circuit behavior. Before Arduino and microcontrollers became popular, the 555 timer was the heart of electronics projects. The 555 timer has three operating modes: Bistable, Monostable, and Astable mode. Let's take a closer look what's inside the 555 timer and explain how it works in each of these three modes. Here's the internal schematic of the 555 timer, which consists of 25 transistors, 2 diodes and 15 resistors. Represented with a block diagram, it consists of 2 comparators, a flip-flop, a voltage divider, a discharge transistor, and output stage. The voltage divider consists of 3 identical 5K resistors, which create 2 reference voltages, at 1/3 and 2/3 of the supplied voltage, which can range from 5 to 15 volts. Next are the 2 comparators. A comparator is a circuit element that compares 2 analog input voltages at its positive non-inverting and negative inverting input terminal. If the input voltage at the positive terminal is higher than the input voltage at the negative terminal, the comparator will output 1. Vice versa, if the voltage at the negative input terminal is higher than the voltage at the positive terminal, the comparator will output 0. The first comparator negative input terminal is connected to the 2/3 reference voltage, at the voltage divider and the external control pin, while the positive input terminal to the external threshold pin. On the other hand, the second comparator negative input terminal is connected to the trigger pin, while the positive input terminal to the 1/3 reference voltage, at the voltage divider. So using these 3 pins, trigger, threshold and control, we can control the output of the 2 comparators, which are then fed to the R and S inputs of the flip-flop. The flip-flop will output 1 when the R is 0 and S is 1, and vice versa, it will output 0 when R is 1 and S is 0. Additionally, the flip-flop can be reset via the external pin called reset, which can override the 2 inputs, thus reset the entire timer at any time. The Q-bar output of the flip-flop goes to the output stage or the output drivers, which can either source or sink a current of 200 mA to the load. The output of the flip-flop is also connected to a transistor that connects the discharge pin to ground. Now let's make an example of the 555 timer operating in a bistable mode. For that purpose, we need 2 external resistors and 2 push buttons. The trigger and the reset pin of the IC are connected to VCC through the two resistors, and in that way they are always high. The two push buttons are connected between these pins and the ground, so if we hold them push, the input state will be low. Initially, the two comparators' outputs are 0. Thus the flip-flop output, as well as the output of the 555 timer are 0. If we press the trigger push button, the state that the trigger input will become low, so the comparator will output high and it will make the flip-flop Q-bar output go low. The output stage will invert this, and the final output of the 555 timer will be high. The output will remain high, even when the trigger push button is not pushed, because, in that case, the flip-flop inputs R and S will be 0, which means that the flip-flop won't change its previous state. For making the output low, we need to press the reset push button, which resets the flip-flop and the entire IC. Next, let's see how the 555 timer works in a monostable mode. Here is an example circuit. The trigger input is held high, by connecting it to VCC through a resistor. That means, the trigger comparator will output 0, to the S input of the flip-flop. On the other hand, the threshold pin is low, and that makes the threshold comparator output 0 as well. The threshold pin is actually low, because the Q-bar output of the flip-flop is high, which keeps the discharging transistor active. So the voltage coming from the source, is going to ground through that transistor. In order to change the 555 timer output state to high, we need to press the push button on the trigger pin. That will ground the trigger pin, or the input state will be 0, thus the comparator will output 1, to the S input of the flip-flop. This will cause the Q-bar output to go low, and the 555 timer output high. At the same time, we can notice that, the discharge transistor is turned off. So now the capacitor C1, will start charging to the resistor R1. The 555 timer will remain in this state, until the voltage across the capacitor, reaches 2/3 of the supplied voltage. In that case, the threshold input voltage will be higher, and the comparator will output 1 to the R input of the flip-flop. This will bring the circuit into its initial state. The Q-bar output will become high, which will activate the discharge transistor, as well as, make the IC output low again. So, we can notice that, the amount of time the output of the 555 timer is high, depends on how much time the capacitor needs to charge, to 2/3 of the supplied voltage, and that depends on the value of both the capacitor C1 and the resistor R1. We can actually calculate this time, with the following formula. Next, let's see how the 555 timer works in an Astable mode. In this mode, the IC becomes an oscillator, or so-called free-running multivibrator. It doesn't have a stable state, and continuously switches between high and low, without application of any external trigger. Here's an example circuit of the 555 timer, operating in an Astable mode. We only need 2 resistors and a capacitor for this example. The trigger and the threshold pins are connected to each other, so there is no need of external trigger pulse. Initially, the voltage source will start to charge the capacitor through the resistors R1 and R2. While charging the trigger, comparator will output 1, because the input voltage at the trigger pin is still lower than 1/3 of the supplied voltage. That means, Q-bar output is 0 and the discharge transistor is closed. At this time, the output of the 555 timer is high. Once the voltage across the capacitor reaches 1/3 of the supplied voltage, the trigger comparator will output 0, but at this point, that won't do any change as both R and S inputs of the flip-flop are 0. So the voltage across the capacitor will keep rising, and once it reaches 2/3 of the supplied voltage, the threshold comparator will output 1 to the R input of the flip-flop. This will activate the discharge transistor. Now the capacitor will start discharging, through the resistor R2 and discharging transistor. At this time, the output of the 555 timer is low. While discharging, the voltage across the capacitor starts to decline, and the threshold comparator starts to output 0, which actually doesn't do any change, as now both R and S inputs of the flip-flop are 0. But once the voltage across the capacitor drops to 1/3 of the supply voltage, the trigger comparator will output 1. This will turn off the discharge transistor, and the capacitor will start to charge again. So, this process of charging and discharging, between 2/3 and 1/3 of the supplied voltage, will keep running on its own, thus producing a square wave on the 555 timer output. We can calculate the time the output of the IC is high and low, using the following formulas. The high time depends on the resistance of both R1 and R2, as well as the capacitance of the capacitor. On the other side, the low time depends only on the resistance of R2, and the capacitance of the capacitor. So, if we sum the high and low times, we will get the period of one cycle. On the other hand, the frequency is how many times this happens in 1 second. So 1 by T will give us the frequency of the square wave output. If we make some modifications to this circuit, for example, change the R2 resistor with a variable resistor or a potentiometer, we can instantly control the frequency and duty cycle of the square wave. Now, let's make a real project to control DC motor, using 555 timer. Here's the components we're going to need to build DC motor controller. We require a 555 timer, a 100K linear potentiometer, 1 MOSFET, 1K resistor, 3 diodes, 2 capacitors, 9 volts battery, DC motor, and a power source for DC motor. Here's the circuit setup diagram. We're using the 555 timer in Astable mode. Here's my motor circuit on the breadboard. I can control the motor speed with this circuit. I'm building this channel to make electronics simple and practical, so if this 555 timer video helped you, support the channel by subscribing and sharing this video. Your support directly helps me create better tutorials. Thanks for watching.